Hello all. The topic for our today's discussion is HDL, Hardware Description Level Language for your sequential circuits. In the earlier session, we have described about what are the different types of modelings that is possible as of the combination circuits about. As we have already discussed in Verilog module, okay, we are having three types of modeling. One is called as your data flow modeling, and next one is called as your gate level modeling, okay, and the third one is called as your behavioral modeling, okay. All these three types of modeling could be used as of your combination circuit is about. But whereas when we come into the sequential circuit, behavioral modeling is highly used and predominantly used, because here always we have some notations or some points which is to be stressed more or which is to be given some importance of high specificity. The sequential logic in Verilog can be given as it defines the flip-flops, latches, and as well as the finite state machines in broad. Okay, the flip-flops, we know that it's a memory storage element, okay, which is working with the concept of your clock, and the latch is called as it's also a memory element which uses with the concept called as your enable signal is there. And finite state machine means it will be having an say for example n number of states, how the level gets crossed from your one level to another level and everything that is studied with this finite state machine. Okay, these flip-flops are called as your edge triggered. It can be triggered either with a positive edge or a negative edge, and these latches are called as your level triggered devices. With the help of your enable signal, it can be an high level triggered device or else low level triggered device. And as of sequential logic is okay, is triggered by a clock event. Okay, latches are sensitive to level to the signal as we have seen, and flip-flops are sensitive to the transitioning of the clock. Okay, so combinational constructs are not sufficient. We need constructs such as your combinational constructs means they are mentioning about the data flow and as well as your gate level modeling is about. But whereas we always need two types of constructs as of this behavioral as of this sequential is about. One is your always, and next one is your initial. Okay, some conditional statements are required as we see in the basic programming papers of your if else, okay, and as well as your for loops and as well as your uh, some other statements for your long jumps and your short jumps and everything, right? So like this, here for this sequential logic we need some conditional statements of your always statement is there, okay, and some in some parts we are using your if else statements too. And always the statements defining process, always it means here we have to given sensitivity list. In the previous combination circuit programming itself, always at an input is given means your output will get changed only when that particular input is changing. Says that sensitivity list, it can be a single element or it can be a multiple element. The change on that element will be okay, will make some changes in the output. Okay, so when the event in the sensitivity list occurs, okay, whenever the event in the sensitivity list occurs, the statement is executed. Okay, so let me take a basic example of a D flip-flop. A D flip-flop will be having a single input, but whereas it will be having two outputs. One is called as your Q and Q bar, and we'll be having a clock. It can be a positive edge clock or else a negative edge clock. Here we are taking that to be a positive edge clock here. So your inputs and outputs are your clock is an input, and as your D data is an input, and your Q is your output. So your input is your clock comma your D, and your output is called as your register Q, because here it has to store the information, right? So register is to be given stressed again, and always at the sensitivity list is your positive edge clock. If it is a positive edge clock, whatsoever the input you give there, that will be fetched as your output here. So Q is equal to your D and N module. Okay, so here we can be pronounced as your Q gets the value of the D. Okay, and here this is the example, the same one is given, and this is called as a sensitivity list. Here the positive edge clock is the sensitivity list. On the positive edge, when the positive edge is detected, okay, the value of the D is copied to your Q. Okay, and here this is an statement of assigning. Okay, assigning is not used within always blocks. Within always block we don't want to use assign, because if this condition has been is executed, then surely this will get assigned, so no separate assignment is required. Okay, and here whenever we are having the inputs is changing, okay, input is an array of change means then we have to represent that with an array from your 0 to 3. It means that q0, q1, q2 and q3 4 changes, and depending on that, if the input changes in 4, then your output will also be changed in 4. Okay, so that's it about. Okay, so the previous things whatever we have discussed is about the synchronous model, which will be only depending on the positive clock alone. So when it's on the asynchronous reset, okay, the positive edge clock or the negative edge means your reset. Okay, so if at always at positive edge clock comma your negative edge reset begin, if reset is equal to 0, if reset is pressed as 0, then your q will be asserted as 0. Else if reset is not pressed, then your q gets the value of your d. And this is again an asynchronous reset. There it happened in one way. See, begin and end. Okay, and here also this begin and end is called as your this is always a pair. This begin and end should be always a pair. In this example it was not necessary, but it has been used because always that means if this is not executed, surely else this will be executed. Here it is not necessary, but whereas always this begin and end will always occur in pairs. Okay, so if the reset is equal to 0, q is equal to your 0. This is the asynchronous reset, as the reset does not care what happens with the clock. It won't depends on the clock. If the reset has been asserted, okay, if the reset is equal to 0, q is equal to your 0, because reset is a low level signal. And this also on the synchronous reset. Okay, synchronous reset means you don't want to give any reset values. You don't want to give the condition to be on the always at statement. Simply we can give it as if reset is equal to 0. This is for synchronous reset. For asynchronous reset, we have to give it as your negative edge reset. A statement is to be given as a condition there. Reset only happens when the clock rises. Okay, when the clock rises. So this is with your enable and reset. Enable and reset means this is for a not for a flip flop. This is for a latch. Okay, if you are having a latch means, then we can say that else if enable is there, okay, then q is equal to q gets the value of your d here. Note that en signal is not in the sensitivity list. Okay, en signal may not be want to be all the things may not be in the sensitivity list too, but we can execute with that. And this the diagram is shown as an what to say, a latch, a d latch, which will be having if clock, okay, q gets the value of your d. And here the sensitivity list is you are always at your clock comma your d. Whenever your input changes, your output will also come to the output. Okay, and the flip flops, different types of flip flops we have seen is the basic itineraries I have written here with asynchronous and as well as your asynchronous mode in common. This will help for examination. Module D flip flop, your input is your clock and reset and your data and as well as your q. So the input and output is defined, and always your output here, this is an memory storage element, right? So it's your register of your q, always at positive edge clock or negative edge reset. If reset, okay, of your q, your 1 bit, your q will be equal to 0. Your output has been, your no previous state is there, it has been reset to 0. Else q is equal to your d. Okay, else your q is equal to your d, that is your q gets the value of your d. For a t flip flop, okay, again it's called as your always at positive edge clock comma your negative edge reset. If the reset, q is equal to 0. Else if t, okay, if t, your q is equal to your negation of your q. It's a toggle, right? So the output will get toggled, okay, when it finds an necessary input of your t is equal to 1. Okay, else q is equal to q only. It will be in the same state as that of the previous state. If your t is equal to 1, it will toggle to the next level. And this your jk flip flop. Jk flip flop means here you are having j and k are the two inputs, and your clock is the another one input, and your reset is there. So here input and output statements are assigned, and your here your output is mentioned with your register. Always at here also it's called as your synchronous clock. Okay, synchronous mode is used. If reset means q is equal to your output will be asserted as 0. Else begin, there are multiple cases, 4 cases there, because you are having two inputs, right? 0 0 0 1 1 0 and 1 1. If you 0 0, it will be as of your truth table, it will be in the previous state itself. So q is equal to q. If it's 0 1, then your set and as well as reset, right, as of j and k. That means instead of j we can write as s, and instead of k we can write as, take it as your r. So here your set is equal to, Here your set is equal to 0, so your q is equal to 0. Here set is equal to 1, q is equal to 1. If it is both are 1 and 1, then as of your SR flip-flop is about, that's an indeterminate state, but whereas here in JK flip-flop, it will just toggle. Okay, what was the previous output? Say the previous output is 0 means, then the current output on 1 and 1 is called as your 1. Okay, and this is your end case. This is the case modules that is used inside this always at statement. And as of counter, the next type of circuit is called as your counter. It's a 2-bit counter. In 2-bit counter, it can count from your 00 to 00 to 11. Okay, it can count from your 00 to 11 if it's clear. Okay, if it's clear means if clear signal is asserted, it's a positive edge clock comma your negative edge clear. In the flip flops, we will be using reset signal, but whereas in as of the counter support, we will be using clear signals. If the clear is given, okay, then your output will be traced as your 2 bits of your 00. Else, if clear is not asserted, your output is equal to output plus 1. And this is a 2-bit register. This is also in storage element. Your input and input clock and clear, and your outputs are your inputs are your clock clear, and as well as your input, and the output is your 2-bit, which is called as your 0 is to 1. Since the 2-bit register, it's in the name itself, it has mentioned as 2-bit register, we are writing it as your 0 is to 1. If it is mentioned as n-bit register means, then 0 is to n minus 1, because we are including 0 here, right? So 0 to n minus 1 counts for n-bit register. So always at positive edge clock comma your negative edge clear. Okay, if it's clear, your output is equal to 2-bit, that is your 00. Else your output is equal to your input. It's just an storage, it won't count up or down, it's just a storage storing the value alone. And the various summary points that we have to take is your sequential circuits are always, sequential logic will always be written in behavior module, that too in the always block. Okay, within the always block, we can use the we don't want to use the assign symbols, because if else loop can be used. And next one is, it should be always the output should be declared as an registers, and whatsoever the sensitivity list is to be embarked inside the always column. Okay, and as of the final state machines is about, there are 3 levels. One is called as your next state logic and state register, and as well as your output logic. Your next state logic, and this is your state register. Okay, precursive state register, and this is your output logic. As of we can take the final state machine as your divide by 3, which is having 3 states, your S0 to S1, S1 to S2, and your S2 to your S0. This is 3 state. Okay, so the first one is called as your where we are defining the states, your input clock, your input reset, and your output Q, and the parameters are your S0, S1, and S2 as your 0, 0, 0, 1, and 10. And the FSM in Verilog can be given as your here, as in the previous registers, positive edge clock comma your positive edge reset. If reset means it will be coming to the state S0, else your state is equal to your next state. Okay, and for example, always at statement, the conditional conditions can be given as your S0, S1, and S2. The case statements are here. If your S0 means, then your next state is equal to S1, and S1 means your next state is S2, and your S2 means your next state is equal to S0, and the default case is always your S0. Okay, and this is the output assignments. Your assignment of your Q is equal to your state is equal to your S0, and this is the final programming with which we are finding one is your state register and your next state logic, and next one is called as your output logic. Okay, so with this we have, and there is one other thing which is called which is about your shift registers. Okay, the shift registers, as of shift registers is about, we can take up the one register is called as your universal shift register. When we go into the universal shift register, we can write the code as, the code is like the same, the initial assignments and the state assignments, and finally as of the universal shift register is about, it is having 2 things. One is called as your left shift and right shift, and another one is called as your loading. Okay, loading the input, left shift and right shift. So here we can say write as initially it will be a universal shift register is your clock and your reset and loading, shift right, shift left, all the inputs has been given, and finally always at this your state assignments. Okay, so positive edge clock or your positive edge reset. Okay, so when it's when your 2 bits are your after loading input. Okay, when your 2 bits are your 0, 0, it's shift left. Okay, when 0, 1 is called as your shift right, and your 1, 0 is called as your, it will be rotating left, and your 1, 1 is called as your rotating, right? So with this we have studied about the large register, that is called as your universal shift registers, which will be having totally 5 operations in total. One is your loading input, shift left, shift right, rotating left, and as well as your rotating right. And next one is called as your up slash down counter. We have studied about the 2-bit counter, and this up slash down counter is, so module up slash up down counter, you will be having your clock reset up UD and as well as your out. So here we can see that always at positive edge clock comma your reset comma your UD. If the reset is equal to 1, your output will be, okay, your output is equal to your 4 bits, that is 0. Else begin if UD is equal to 1, out is equal to, okay, if your up slash down is equal to 1, output is equal to your output plus your 4 bit of 0001. Else your output is equal to out minus this and down count. If its UD is not equal to 1, if it's 0 means, then your out is equal to out minus your 4 bit of your 1. This is your end module. And finally the mod 10 counter. Okay, in this mod 10 counter what we have to do is, see, the logic is the same. So the module mod 10 of your reset clock comma your the state assignments, and always at positive edge clock only it will do. So if reset is equal to 1, if reset is equal to 1, then what you can do is your output is equal to 4 bit of your 1001. Okay, so that means when it counts to your 1001, okay, that means your mod 10 counter means it will count from your 0000 to 1001. So if your value is equal to, if it reaches 1001, then it will be automatically resetted. Else if it had not reached the value of your 1001, okay, your output will be incremented by 1. Your output will be incremented by 1. Thank you. So what is the overall things we have studied in this HDL for the sequential logic is, we have studied about the basic fundamental flip-flops, a model latch, and about the counters, okay, and as well as shift registers, and finally the